In this video, we'll take a look at the angular momentum of rigid objects. So in our first example, our system are these two balls of dough on the outside edge of this rod. If we want to give this thing a small angular momentum, we can think about what options we have. If we want to give it a small angular momentum, we could try to spin it slowly about this central axis. We could also move these masses in, so the position of these relative to that center point is smaller. And now if we spin, it's got a small angular momentum because it's got a small moment of inertia, a small rotational inertia, and a small angular speed. If you want to give it a larger angular momentum, we can move these back out, maybe a bit farther than they were before, and we could try to get it to rotate at a greater speed. That would increase the angular momentum of this system. In these examples, we've been continually going clockwise, and clockwise angular momentum would end up being a negative angular momentum for our direction choices. So our system is now this bicycle wheel, and if we have it rotating in this manner, it has an angular momentum that's equal to its rotational inertia times its angular speed. If we want to change its angular momentum, we could also change the mass. If we add additional masses to the edge, like this, in a manner somewhat similar to what mechanics do when they balance your tires, we can now get it spinning again. It's got a new angular momentum. Even if the angular velocity is the same, it's got a new angular momentum because it's got a different mass. So its rotational inertia is now different. It's spinning in this counterclockwise direction, and counterclockwise directions are generally taken to be positive in our course. We could also spin it in the clockwise direction. Spinning in the clockwise direction, it has a angular momentum in this direction. This clockwise direction is taken to be negative. So the angular momentum of this object doesn't depend solely on the angular velocity. It also depends on the shape of the object and how the mass is distributed in that object. So the angular momentum can be either positive or negative. It's positive if it's going in the counterclockwise direction, and it's negative if the object is revolving or rotating in the clockwise direction. So we're back to angular momentum being equal to the rotational inertia of the system times the angular velocity. That's the same relationship we used when we were talking about objects orbiting some central point.